Hey everybody, my name is James Wadhwani. This year, 2025, I'm the lead of R&D, Research and Development for Purdue Aerial Robotics team. I wanted to do kind of a quick little class on, well, I say little, it's going to be a lot of videos on virtually everything in aircraft design. Um, this will include X-Flyer. Hopefully somebody makes a video about SolidWorks too. The idea behind this is we had the exploration sessions, but due to a variety of reasons, people being busy, classes just starting, a lot of people didn't actually make it out to the plane design exploration session. So I found that I've had to kind of re-explain a lot of things. So I thought it'd be helpful just to get a video down or a series of videos so that people can reference these, right, and have explanations for these slides that we've already made. So let's go ahead and get into it. Today, we're going to be talking about kind of the basics of aircraft, right? Kind of just how they work. I'm going to quickly go through the slides so that you guys can see what's in this. It's relatively simple. There are some more complex topics, but if you're looking through this here and you feel like you know everything here, right, then um, go ahead and skip this lecture, right? I mean, this is pretty elementary stuff, but I will get a little bit into some more complex sides of it. Okay. So with that being said, let's go ahead and dive in here. So starting off with the basics, right? Let's talk about how a plane actually looks and all its components. You might be thinking if you are a pilot or you're really into planes, who the heck doesn't know this? But a lot of people don't, and it's good to cover a solid basis to move on from. So this right here on the left, we see, if I can draw here, beautiful. We see what is, looks like a conventional single engine plane, maybe a Cessna 172 or something like that, right? The core component here is the fuselage, all right? Now that is the main body of the aircraft. This is where all the magic happens, all right? This includes where your payload might be, your occupants of the aircraft, so your pilot, your passengers, they'll likely sit here. It has a lot of your components. It would house, in a lot of planes, it houses the engine in these single engine planes. So your power plant, as well as any avionics, kind of the core structure of your plane. Here we have the main wing, right? Kind of important. I hope you have a main wing on your plane. And this provides the main source of lift, right? So you get a lift vector going up from this wing. Okay. Here you have your tail or your empennage, two kind of different names for it. This includes what's known as the horizontal stabilizer, which is this right here, which is kind of just a smaller wing, if you really think about it. But often those actually provide downforce instead of lift, so kind of a negative lift for in order to stabilize planes. Here we have the vertical stabilizer, um, which is the actual surface, kind of lifting surface vertically placed to provide some stability in the yaw and the roll axes. Okay. Now, these often get confusing. Some people call the entire vertical stabilizer the rudder. That is not true. The rudder is only the movable surface, control surface at the back. And some people call the entire horizontal stabilizer the elevator. That is also not true, right? The elevator is just the movable control surface back here. Okay, these two guys. So those will deflect up and down, and we'll get into that. The ailerons are the movable control surfaces for the main wing. Okay, so ailerons, these will change your roll of your aircraft. So it'll kind of roll around like this, right? Um, and the elevators can command your pitch. Okay, so they'll change kind of the lift on the rear, and the nose will come up or it'll come down. And then your rudder controls your yaw, which is also known as side slip, which we'll get into more. We have flaps here. This is a little picture I have of a Spitfire because it's a cool plane. You can really see the flaps. These are very, very heavily deflected flaps. And these are used for your critical phases of flight where you want to have more lift, right? They actually increase the amount of lift on a wing, which we will talk about later. So, if you have a plane, specifically for us with our seaplanes, competition last year didn't have flaps on their plane because they're a little bit lighter and they had a lower wing loading, right? So they were able to take off in their runway distance without the need of flaps. Dodo, the research and development plane, the VTOL one, did use flaps. And the reason for that was, well, we wanted our stall speed to be low so that when we're transitioning, we wouldn't have to go quite so fast to get into a full transition from vertical to horizontal flight. And so by using flaps in that way, we're able to bring down that stall speed by increasing how much lift our wing is actually making. Okay. All right. I think I've covered that pretty well. Let's move on. Here we have the rotation axis of the plane. Okay, so let's start off with the roll axis. You can see this right here. Okay, this is this blue line coming out of the plane, and this is often called the longitudinal axis as well. And like I said earlier with ailerons, this is kind of the axis that a plane will roll around when you deflect your ailerons here and here. Okay, um, so there you can see the direction of positive roll. Okay, as you roll to the right, that's positive roll. The next axis is the yaw axis. This is also known as the vertical axis, and that's this guy right here. Again, yawing to the right is positive yaw. Okay. And then finally, we have our pitch axis right here. Okay. And pitching up is positive pitch, and that's done by the elevators right here. Okay. Um, yaw angle, like I said, is called beta, also known as side slip angle. Interestingly enough, which we'll get into more, a positive yaw angle, so a positive beta, is actually airflow from the pilot's right. So it would look like, if we're looking at this picture here, it would look as if the airflow were coming from here, okay? Now, if you think about how your plane is side slipped at that point, right, that means that your plane is traveling in this direction, and so you're actually facing to the left. So that's a little bit confusing. It's something you guys need to keep in mind here is a positive beta, so a positive side slip angle, if you're kicking out the plane, kind of drifting it in the air, is actually your plane facing to the left. It's wind coming from your pilot's right. Okay? And here on the right here, you can kind of see what I was talking about overall with the ailerons changing your roll, your elevator changing your pitch, and then your rudder here changing your. So I hope that makes some sense. There's a lot of, you can just look up videos of planes flying and have a look at those control surfaces moving. There's a lot of different ways you can figure out about, kind of how these work. But really this slide, the important part is keeping in mind this figure right here. And our pitch angle, which I should have said before, is called angle of attack or alpha. So you'll see AOA and alpha being used interchangeably, and we'll get into more of what that means a little bit later. So an airfoil, right? What is an airfoil? I see a lot of people confusing an airfoil and a wing. All right. So these slides were kind of made for teaching this in person. So, we have this kind of open-ended question. What's an airfoil, right? How's it different from a wing? Well, I'll go ahead and tell you guys. The airfoil is a 2D cutout of a wing. Okay, so here we have basically a plane, not an airplane, like a data plane going through the wing. All right, and your wing is your 3D shape here. Okay. And this plane, if you were to take a little cutout and go into the second dimension here, teleport yourself to the second dimension, we have the airfoil, right? And that's just the cross section of the wing at a certain point. So this airfoil for this specific plane that we have here, it kind of changes throughout the wing, right? So you have a bigger airfoil here, right? If you were to take another datum plane right there, slightly smaller here, and it kind of decreases and comes this airfoil that it shows in the cutout, right? So keep in mind, all right, probably the most important thing from this slide, wing is the 3D shape. The airfoil is the 2D cutout that determines the cross section of the wing. So if we were to look at this wing directly from the side, you'd see it shaped like this, okay? That's a terrible drawing, good lord. But yeah, this is our airfoil, okay? They're generally shaped like this, kind of like a curved teardrop. Um, and that's the most important thing here, okay? So let's move on. So yeah, like I said, airfoil, 2D cross section of a wing. Big difference between a 3D wing and a 2D airfoil, right? So there's different aerodynamic characteristics. When you get 3D geometry, you get things such as wingtip vertices, which we'll talk about in the aerodynamics section, which actually reduce the overall amount of lift coming from the wing, all right? And there's also different uses to study these, right? When you look at your airfoil selection, which you should be doing early on in your design process, you want to be looking at your coefficient of lift and your coefficient of drag and the efficiency of your wing, which is your CL over your CD, okay? And you want to be looking at that through the airfoil, right? The 2D cutout, because that geometry determines how your wing is going to interact with the air. So we would look at an airfoil like this and we'd say, okay, well, this NACA 6415, which is a type of airfoil, it's just numbers, which we'll get into, showing how an airfoil looks. And you see that NACA 6415, you say, okay, well, this NACA 4415 has lower lifts at a certain angle of attack. So that way you can kind of look at the different airfoils and determine which one would be better for your wing, right? Generally, you want to look at a high efficiency airfoil, or if you're doing kind of a short takeoff plane, or like Dodo was, where we wanted low stall speed, you would be looking at a high cambered plane. Okay. So let's go into airfoils in general here and what they kind of look like. So important notes here are the leading edge and the trailing edge. Okay, the leading edge is the farthest most point that you can physically get on the airfoil. The trailing edge is the farthest aft or rearward point. Okay, you have an upper camber, this top surface here, and you have a lower camber right here. All right, those don't really matter. What matters here is the mean camber line, which is this line right here. Okay, the kind of curved line. This is actually the average between the top and the bottom at any given point. All right, pretty much all airfoils are positively cambered, so this line is going to be going up like this. If you had an airfoil that's negatively cambered, you might be you'd really just be flipping an airfoil over, right? So we don't really see that. And then this is our chord line. All right, so the chord line determines the length of the wing from the leading edge to trailing edge. And this is just the straightest line you can make. So if you had a pretty stupid looking airfoil where you had a lot of camber on it, right, that camber line was very extreme, you might have an airfoil that looks like this, okay? And your camber line would still follow that curve up around because it's the medium of the top and the bottom camber, but looking at the leading edge here and the trailing edge here, your chord line would actually come outside the wing and go like that along the bottom, right? Because that is the straightest line from the leading edge to the trailing edge, okay? So moving on. Um, Here we have kind of our first complicated concept. Now you'll notice I left this slide blank, partly because I'm lazy, I didn't want to fill it out, and partly because I like drawing all this out and kind of explain this to you. So the Reynolds number, it's stupid. It's pretty dumb. And I mean that in the best way possible. It is, I love this number. This will keep coming back to you if you do aerodynamics or what have you in the future. Um, so this is a non-dimensional number, right? That's kind of why I think it's kind of stupid. It's non-dimensional. It does not matter. It does not relate to different scenarios very well unless they have the same characteristic length, okay? And I'll get into that. But first, let's discuss it from a high-level point of view, okay? So the Reynolds number, which is known as RE, is equal to the ratio of inertial over viscous forces, okay? Now you might be watching this video, you might be going, oh, I don't need to learn about the Reynolds number. I'll skip this slide. Don't, because you're going to be doing X flyer or you're going to be doing something, some calculations. You're going to go, what the heck is this RE number, right? So inertial versus viscous forces. Okay, what do I mean by that? Well, let's take an example. So the Reynolds number goes to very, very high numbers. Dodo, our RC plane, which flew at about 19 meters per second in cruise, had a Reynolds number of 644,000 at cruise, right? A very high number. Um, you can get easily into the millions with the Reynolds number. But let's look first at a low Reynolds number flow. So what does that mean for our little ratio here, right? That means we have high viscosity if we have a low Reynolds number, okay? So high viscosity, that's not how you spell viscosity. Viscosity, I don't even know if that's how you spell viscosity, whatever, is equal to a low Reynolds number, okay? So let's think of some flows where this might happen. First off, kind of the example I like using is a faucet, right? So if you have a faucet, let's draw out a faucet here. Look at that, I'm a great artist. Okay. And you slightly open this guy right here, this little handle, slightly crank that thing open. It's going to have a very slow stream. In fact, it might kind of drip drop out of there. All right. This is a low Reynolds number flow, right? You have a very low velocity. And this means that viscous forces are taking hold, right? So every single drop comes out like a teardrop. Why does it come out like a teardrop? Because that is the shape that water assumes when you have kind of the viscosity from air on either side, forcing it into the shape. All right. Another example might be flow on a rock, right? So this is kind of a rock, and you drop a bit of water onto it, and it flows down in kind of a zigzag pattern, right? Because of the viscous effects of the rock, right? Minute bumps in it, maybe more friction at a certain point. That drop is going to be kind of changing its direction of motion. Okay. This is actually the same thing as why rivers kind of meander and curve like this is because of viscous effects, right? They'll change their flow one way or the other throughout their lifetime. Okay. So that's a little tidbit of information. You didn't even know that. Anyway, now let's look at high Reynolds number flows, okay, in the millions. So this is where you have high inertia effects, all right? And this is where your flow might be more turbulent. And real quick, the difference between turbulence and laminar flow is that laminar flow is sort of made up of streamlines that are consistent and uniform with each other. Okay, so it's like if you had, oh, what the heck are we doing here? If you had flow in a wind tunnel, right? You want that to be laminar. Flow in maybe a pipe, right? If it's kind of slow flow, that's going to look laminar. Basically, it's orderly. You know what's happening, and the streamlines are kind of layered on top of each other. Turbulent flow, on the other hand, well, we have no clue what's going on there, right? Very hard to figure stuff out. The streamlines are overcrossing each other. You have vertices. You have crazy airflow. Okay, and that would be at a high Reynolds number when kind of the inertial effects overtake and create turbulence. At those lower Reynolds numbers, you see more laminar flow, like on this rock or the drops of water coming out of this faucet, right? So anyway, that's turbulent versus laminar. Let's look at a high Reynolds number flow. Okay, so like a plane. Let's think of our favorite plane here. Oh no, I like the F-35. Let's say you have that wing of that plane, okay? Once again, an airfoil, we've taken that 2D cutout. And you have wind hitting that wing at Mach zero point 0.8, right? So almost at the speed of sound. So it's very, very fast. And you have your airflow getting shot off in different directions, right? Becoming turbulent behind it. This is kind of your high, forceful, inertial Reynolds number flow. Okay. Again, you could, back to the sink idea, you could crank open this faucet like this, and you'd have higher Reynolds number flow coming out of it, really turbulent flow, right? So that's one way to look at it. So now let's go to the math of the Reynolds number, right? So this is equal to rho v L over mu, okay? Mu is your dynamic viscosity. Again, I don't know how to spell viscosity. I think that maybe this is correct. Um, right. So I always get mixed up between dynamic viscosity and kinematic viscosity, right? So this is dynamic. That's what the typing was. I just looked it up. Rho here is our fluid's density. So your fluid here is probably air if we're dealing with aircraft, but it could be water, it could be milk, it could be, I don't know, molasses. That probably wouldn't work so well. But anyway, this is our density, right, of our fluid. Okay, not our surface, of our fluid. This is our velocity, our flow velocity. So for a pipe, it'd be the water flow. For a plane, it'd be how fast your plane's going, assuming that the air is stagnant. And then L is our characteristic length. Well, James, what the heck does characteristic length mean? It depends, right? Two types of people, well, more than two types of people, but there are two types of people who use the Reynolds number, and that's plumbers and aerospace engineers. And for plumbers, right, you'd be looking at pipes. Okay? In this case, your characteristic length is actually the diameter of the pipe, d, right? So their Reynolds number would be rho v d over mu, right? Just replacing that L with d. Um, and so let's say that you have two pipes. Okay, you have a high diameter. I don't even know how that happened. You have a high diameter pipe and you have a low diameter pipe. So this is a high D and this is a low D, right? This is a smaller, thinner pipe. Let's call this D1 and D2. Okay, that's it. Whatever. Can't really see that. High D1, low D2. All right. So you'll notice, right, depending on your velocity, these Reynolds numbers could be the same or they could be different, right? So let's say they were the same. How do we make them the same for flow in both of these pipes? Well, since D2 is lower than D1, we'd have to what? We'd have to increase our velocity. So this means that if this is traveling through at v1 and this is traveling through at v2, then it follows that v2 would have to be higher than v1. Now, this is only for the case that we're trying to match our Reynolds numbers. So a Reynolds number, this will be 1, this will be 2, so that's the convention we're using. Reynolds number 1 is equal to Reynolds number 2, right? That this is not a necessary thing to have happen. Your Reynolds numbers don't have to equal each other. But in this specific case, we're just looking at how we could make them equal, right? So if you had these Reynolds numbers equal, like so, theoretically speaking, the flow through both of these pipes will be the exact same. They will behave in the exact same. Right? You'll have the same ratio of inertial to viscous forces, so your flow will interact with the pipe in the same way. Okay. Um, so that's kind of how it looks with pipes, right? Just to get an idea of the Reynolds number and how that looks in real life. Well, now let's look at airfoils. Okay. So say we had a very long wing on a large plane, and let's say that we want to stick our model into a wind tunnel to test, how it's actually going to look. And we're actually doing this for the first time this year in part. So the wind tunnel, the Boeing wind tunnel is 4 feet by 6 feet for the cross section. Okay. We're looking at doing a 7 foot wingspan for a drone, roughly. So that means we would have to downsize the size of our plane to fit it in the wind tunnel. We have to do a little mock smaller plane. Okay. It's kind of terrible drawing, but let's redo that. Okay. So let's say that this is our wing one and this is our wing two. Okay. And our second wing is going in the wind tunnel. Well, how do we make sure that our results are realistic to what we'd see in real life? Well, looking back at the pipes, right, you want the same interaction of airflow. So you want your RE1 to equal to your RE2. Okay, same thing here. So looking at our chord length, which by the way, now our equation is rho VC for L. Our characteristic length is our chord length. Okay, so this is C1 and this is C2. Okay, now if we want to say, okay, this plane might be smaller, but we want to see the same effects as it would have in real life, then we need to do something about our velocity. Or we could do something about our density, but generally, sorry, I don't know why I wrote RE there, that should be mu. Generally, our density and mu here are properties of the air, right? They're things we can't change. So we're looking here at the two things we can actually change. So for a wind tunnel, we might want to crank up that velocity to be a little bit higher, right? So V2 should be higher than our flight speed, which is V1. And then theoretically, once again, all theoretical, theoretically, we would get the exact same results and the exact same coefficients of lift and drag and moment out of our wind tunnel models we would for the actual plane. So when you're doing X-Flyer and you're thinking, you know, what the heck is my Reynolds number? First, calculate it using this. Make sure L is the chord length, so the length of your wing. And if you have a variable chord, it's going to be your mean chord length, your mean aerodynamic chord. And ask yourself, does this make sense, right? And why are we putting in the Reynolds number? So that X-Flyer knows how to have the air actually interact with the wing. Okay? So that's a bit about the Reynolds number. I think I covered that pretty well, to be honest. Let's go into the coefficient of lift, right? Coefficient of lift. This is a dimensionless number, and this is probably the most important number you're going to see with, starting your aircraft design. All right. So we all know that a plane generates a certain amount of lift, right? A certain amount of vertical force. Ignore this equation for first. Let's look at this equation here. CL equals 2L divided by rho V squared A. Okay, A here is the area of your wing. Rho is once again density. V is your velocity, and L is your lift. Okay, not to be confused with length. This is your lift. It's a force. Now, coefficient of lift, just like the Reynolds number, is dimensionless. All right, we love dimensionless numbers in aerospace engineering because you can apply it to any situation so long as you're able to add a dimension to it, right? So this is how people figure out the amount of lift that a wing can make, right? Aerodynamics is stupid. Nobody knows what they're doing. And to be honest, this is the best way you can figure out the lift for a plane is by at some point just sticking something in a wind tunnel and doing your own, empirical gathering of data. So we've stuck a plane into a wind tunnel. We've calculated its CL by using the area of the wing that we have and the amount of lift that it's generating, right? And now we have the CL number for a plane. for an airfoil, right? Um, I should note if you see a C small l, that's generally lift for an airfoil. Then if you see big L like this, that's lift for a plane, like a whole plane, okay, whole aircraft, right? Like, and I mean a wing by that, right? Like a 3D wing, okay? So keep that in mind. So what a scientist does, or an engineer, how someone figures out the amount of lift that an airfoil is going to create is they stick in the wind tunnel and they calculate the CL based off those values. All right. And that again is dimensionless. So no matter how big you make this airfoil, the dimensions of it, how big your wing's going to be, it should have the same CL at the same angle of attack. All right. And we'll get into that later too. Um, So then you take the airfoil, you put it onto your plane, and now you say, okay, because the airfoil's already been dimensionlessly, found to have a CL in the wind tunnel of X, so and so. Now we can put that on our plane and say, all right, here's the total lift of our plane based on the CL of the airfoil, and then the flight speed and area and wing area and density and yeah, density of the airflow for our actual plane. All right, so CL is we have this nice quote up here. This is right, right? It's a dimensionless number that quantifies how effective a shape like an aircraft wing, or more so like an airfoil, is generating lift. And it only depends on wing shape and angle of attack. All right. So wing shape, yeah, wing shape's already defined. Obviously, it's the geometry of your wing. The angle of attack, we'll get into that and how that affects our CL in a second. Okay. Let's see. I think I covered this pretty well too. Moving on. Coefficient of drag is the exact same thing. You'll notice same exact equation. Again, everything's stupid and makes no sense, but this is nice, right? You just have your CD. CD is coefficient of drag. It's just like CL. It's found the same way that CL is found. And then you can use that to find drag in your whole wing, right, after seeing what it is for the airflow. Okay. So let's do a little talk here. I forgot about this guy. Right, so we're thinking here. We're thinking, which one has more lift? Now I'm going to give you a little bit of. Oh, actually, you know what? We'll get into this. Let's just see if you guys can figure this out. You have 5 seconds. All right. In 5 seconds, you say, is it the 6415 or the 2415? Right. So 5, 4, 3, 2, 1. If you said the 6415, you'd be correct. Right. Why? Let's see if we go into why. Nah, we kind of go into why. Well, why does this happen? Right. This is because this airfoil is more cambered. Okay. If you kind of look at the shape, you can just kind of tell that this thing has more of a higher mean camber line. I don't know why it's bugging out like that as compared to the 2415, right? This one is not quite so cambered. Okay. And that has to do with the difference in pressures, right? As your airflow turns over your wing, so as it kind of hits the wing and goes over the top and over the bottom, you get a pressure differential on the top and the bottom. Okay, and we'll go more into that later. And P2 is generally greater than P1. All right. So you have somewhat of a suction effect on top of the wing and then a kind of forceful effect on the bottom that pushes it up because fluid always wants to go from an area of high pressure to low pressure. So generally speaking, the more camber you have in your wing, the more of that shape there is, you would get more lift. If you had a perfectly symmetrical wing um, with absolutely zero camber, so if I can see if I can draw one, pretty close, right? So your camber line is equal to your chord line, then you would have the exact same pressure on the top and bottom if you didn't have an angle of attack. Okay, so P1 is equal to P2. And then that means you get no lift, right? So the more camber you have, the more lift you get. If you have no camber, you're getting no lift. Specifically at a zero angle of attack. All right, I want to clarify that. Okay, so let's have a look, right? And we were right. So 6415 has more lift. The curve is higher. Now I want to take a moment here to talk about our CL alpha curve. This is one of the most important plots you can see with aircraft, and this determines what your coefficient of lift is at every angle of attack, right? So at every pitch angle, and I'll go more into alpha in a second. But here, right, you can see at 10 degrees of pitch angle, our 2415 is making about 1.25-ish of a CL, while our 6415 is making about 1.6. Does this mean the 6415 is better than 2415? Not necessarily. If you're trying to make a short takeoff plane that has a lot of lift, then yeah, this is probably your better option. But if you want to go for more of an efficient plane, then you'd want to be looking at your CL over CD plot. And then that would tell you, which airfoil is better for you to go with. So just because it has a higher lift does not necessarily mean that it's a better airfoil. Now you might have seen this already. What happens here, right? This is stall. Okay, this is your aircraft actually stalling, which means that the airflow has separated from the airfoil, right? So you can see a non-stalling. Yeah, forgot about this guy, right? We don't want our plane to stall. He's not happy. Our plane is stalling. This airfoil right here has attached flow. You can see kind of that laminar flow going over it, right? Very smooth streamlines, very uniform, very nice. Okay, going back to laminar versus turbulent. So let's say this is like at a 5 degree alpha, okay, angle of attack. Now, when you start hitting about 15 degrees like this, and it's just kind of guessing, but most airfoils stall at about 15 degrees. Um, then you get sort of this detachment of your airflow, right? It gets the physical object in the way of the airflow now has a much larger surface area because it's deflected up. So now all your airflow is hitting this giant surface area and overshooting it and creating these vortices in the middle like this, right? Which are not good. You do not want kind of turbulent vortices. So this ruins the pressure differential because now you have this very energized, higher pressure, stalled out air on top of the wing that kills your lift. Okay, and this is where you see planes kind of fall out of the sky. An important thing to mention is a common thing is called stall speed, right? Planes do not stall because of speed. They stall because if we go back to our CL curve, right? Let's say a plane is heavy enough that it needs a CL of 1.6. Uh, well, it needs a CL of 1 to fly in cruise, okay? Now, in cruise, you're going to be flying along at about a 3 degree alpha, okay? But as you slow down, right, remember the lift equation, lift equals 1/2 rho CL S V squared. I kind of did that order wrong. Let's write this a little better. 1/2 rho V squared SCL. It's kind of the normal convention, right? So as our CL, or excuse me, as our velocity decreases, right? So we're slowing down, approaching what's known as a stall speed, then what needs to go up, right? Well, our density is pretty fixed. Our wing area is definitely fixed. We're not going to go make our wing bigger. I mean, that'd be kind of cool actually, but we're not going to be able to do that. But what needs to go up, right? Our CL, our coefficient of lift, needs to go up. So once you get to a certain speed, um, where you've hit your maximum CL, it's officially the slowest you can go because you cannot get any higher lift out of your wing. Otherwise, you will stall out, right? So just to be clear, there is such thing as a stall speed, but your plane does not stall because of the speed. Your plane stalls because you've hit the critical alpha is what this is called. Okay, this point at which your airfoil stalls, and then your lift goes down, and you no longer have enough lift to sustain flight. That is what stall speed entails. Okay. So moving on, we're going to see a video here of a plane actually stalling. You'll note this yarn that's attached to the wing on by tape, right? This is called a tuft. These are tufts. I had a professor once tell me that if you ever see a company test flying with tufts, that means something has gone horribly wrong during the design process because you really shouldn't have to use tufts in a test flight to determine how your airflow is looking, right? This should be something you can do through computational fluid dynamics or wind tunnel tests. But anyway, it's a pretty cool video here. So you'll see, right? Laminar airflow. Those tufts are very straight. Looks very nice. He's got his flaps down here. That's why there's kind of that gap in the wing. And he's going to pitch up. He's pitching up right now. You hear that stall horn, which tells you when you're about to stall coming in. And those tufts all of a sudden become very turbulent, right? Because the airflow is separated and the plane pitches down. So you can kind of see how that the wing stalls out like that there. So some cool stuff to see. Moving on, right? This is a little talk about the wing. I think this is our last slide for this section. Yep. I don't want Copilot up. I don't know why that came up. Um, so the wing, it's pretty useful, right? I mean, I hope you have a wing on your plane. Otherwise, you might not go anywhere very fast. Important measurements here are the chord length, which we talked about earlier, right? So this is a top-down look at a plane. And if you really wanted to think about it at this point, um, your airfoil is just going to be a straight line because that 2D section is getting looked at from this angle. Um, your chord length, you'll notice here changes, right? You don't have a constant chord length. This is because this wing is tapered. It tapers off. So you will have a difference between your root chord and your tip chord. So when you're doing your Reynolds number calculations, you want to use your mean aerodynamic chord, which for most things is just average, right? If it's a straight taper, it's going to be the average. But there are equations out there for what your mean aerodynamic chord would be based on the type of wing, because you can have elliptical wings like the Spitfire, where you're kind of rounded at the end, and you can have wings that are kind of multiple different tapers. If you were stupid like this, you can have a bunch of different shapes for your wing. Wingspan here is from wingtip to wingtip, right? This is our wingspan, and that's an important number for calculating that lift, right? How much lift you have is determined by your wing area, which has to do with your chord, your mean aerodynamic chord, and your span. Um, so anyway, that's a little bit about the wing, and I know this video was quite long. I hope it was helpful to you guys for getting started. I'll see if I can make the next ones a little bit shorter, but our next video will be going into forces of flight. So make sure that you guys tune into that because we get a little bit more in depth on right alpha, on how lift actually is generated, right? We're going to look at vortices, CP plots, drag, all this stuff, right? So definitely tune into that. So thank you.